All right, here we go. So section 7.5 is on roots and zeros. All right, so a root, a zero, an x-intercept, those all mean the same thing. So root, zero, x-intercept, same thing. So all of the following statements are equivalent. So number one, you could say a real number r is a root of the polynomial, p of x equals 0. You could say p of r equals 0. In other words, that's where it crosses the x-axis. R is an x-intercept of the graph. X minus r is a factor of p of x, because remember, if it was a root, it factored evenly. There was no remainder. When you divide the rule p of x by x minus r, your remainder is 0, and r is a 0 of p of x. So all those things mean the same thing. All right, so we're going to use these statements in order to write polynomial functions with certain zeros. So we're going to have really long polynomials, and we're going to find what their zeros are. All right, the fundamental theorem of algebra says every non-constant polynomial function has, oh, I left something out, has, where a zero may be a complex number, has at least one zero, and that zero could be a complex number. And then the corollary is the one that's really important. So every non-constant polynomial of degree n, so that means its highest exponent was n. That means that you would have exactly n zeros, including multiplicities. So you could have the answer 2, like if I had x to the fifth minus 32 equals 0. 2 could be an answer, but it could be an answer 5 times, right? So including multiplicity. So n was 5. All right, it starts out pretty basic. So solve each equation. This is taking it back to Algebra 1. State the number and type of roots. So solving the first equation is very easy. It's just a equals 10. Okay, so that means there's one solution. Okay, and that solution is a real solution. If you wanted to be even more specific, what would be the most specific answer you could have? So not only real, but whole, even more than that. You guys remember the Venn diagram? Natural. So this would be a natural number. So you could say it's real, rational, integer, whole, natural. All right, I'll just say real or complex. Okay, so the next one. So I have x squared plus 2x minus 48 equals 0. So when you solve this, we're going to try to factor. So we need negative 6 and plus 8. So they multiply to be negative 48, and the outer and inner combined to be negative 2, or positive 2. Equals 0. So you have x minus 6 equals 0, x plus 8 equals 0. So x equals 6 and x equals negative 8. Okay, so this one has two solutions. And those solutions are both real. Okay, number 3, so I have 3a squared plus 18a. So if I was going to solve this, you just pull out a common factor. So they both have 3 in common, and they have an a in common. So when you do that, you have a plus 6 left. So you get a equals 0, right, because 3a was equal to 0. And you have a plus 6 equals 0, so a equals negative 6. So on this one, we have two solutions. And they're both real. Okay, so if you notice so far, we had a to the first on the first one, and we had one solution. We had x to the second on the second one, and we had two solutions. And we had a to the second on the third one, and we had two solutions. So it's following that rule that we said where it's going to have the same number of zeros as its power. All right, so then the next one, if you're solving this one, we actually have to factor. So we have y squared plus 4 times y squared minus 4 equals 0. if you just add 16 to both sides and take the fourth root, you actually miss 2 of the solutions. So we factor. The second one factors into y plus 2 and y minus 2. But the first one is the sum of 2 squares, which we know does not factor. So we leave it as y squared plus 4. So when I set each piece equal to 0 and solve, I have y squared plus 4 equals 0, y plus 2 equals 0, and y minus 2 equals 0. So I get y equals negative 2 and y equals 2 for the last ones. And the first one, if I subtract the 4 over, get y squared equals negative 4. Take the square root, you get y equals plus or minus the square root of negative 4. So how do we write the square root of negative 4? 2i, right? So y equals plus or minus 2i. Okay, so this one has 4 solutions. 2 are real, and 2 are imaginary. So you can say imaginary or complex, it doesn't matter. Because we have 2 here, right? We have 2 and negative 2, and then we have 2i and negative 2i. So we have 2 that are written there. All right, so the complex conjugate root theorem says if a plus bi is a root of a polynomial, so if it's one of your solutions, then a minus bi is also going to be a solution. So imaginary solutions go in pairs. Real numbers don't. You know, if I have the answer 2, I don't necessarily have to have negative 2 as an answer as well. But imaginary numbers always go in pairs. So if I have 3 plus 2i, I'm going to have 3 minus 2i as well. Okay, so that means when you write the simplest polynomial function with zeros of 3i and negative 1, when you see an I solution, you're going to have its conjugate as well. So this means you will also have negative 3i as an answer. Okay. So we did this polynomial function thing last time. So if I have a 0 of 3i, that means I need x minus 3i as a factor. If you have negative 3i, you're going to need x plus 3i. And if you have negative 1, you're going to need x plus 1. Because when you plug those numbers in, you want to get 0 out. All right, so now we multiply out. So again, always think about the easiest way to multiply. If you multiply the I ones together, that's going to make your life a lot easier. If you guys multiplied like x minus 3i and x plus 1 together first, you're going to have a mess. So always multiply your i's together first. So when you do that, you have first terms make x squared, outer is plus 3ix, inner is minus 3ix. We knew those were going to cancel because it was going to be the difference of 2 squares, right? And then the last is negative 9i squared. So those middle terms cancel, like we said. And if you remember from chapter 5, I think, what's I squared? Close. Yep, negative 1. Yep, so you get x squared. Then you have negative 9 times negative 1, so that's plus 9. It's always those like x squared plus 9s or x squared plus 4, like the sum of 2 squares, usually. Not always, but then x plus 1. All right, now you FOIL these out. So first is x squared times x, so x cubed. Outer is plus x squared. Inner is plus 9x. Last is plus 9. That's your polynomial.
How come we used x plus 1 instead of x minus 1?
Because when you plug negative 1 in here, do you see how you get 0 out? So you always want the opposite. It's kind of like when we do synthetic division, we put -1 on there. We put the 0 in that spot of the divisor. Right. So Descartes' rule of signs. All right, this is going to be important when we're trying to find the zeros. It kind of eliminates some different possibilities. Okay, so it's kind of confusing when we actually see it written out. So when you see the examples, I think it will make more sense. So basically, let's suppose you have a polynomial. The number of positive real zeros of f is either equal to the number of variation in signs of f of x or less than that by an even integer. The number of negative real zeros is either equal to the number of variations of sign in f of negative x or less than that to the number by an even integer. So like I said, you guys have no idea what this means right now. That's okay. Okay, so here's what I'm talking about. So we have p of x written, or f of x. You can think of it f, like our example. Okay, you're going to go through and you're going to look at the signs in front of each term. Okay, so this is a positive x cubed, and then we go to a negative x squared, right? So that's a sign change. You went from positive to negative. Okay, but then we go from negative to negative, which is okay. So we're not going to count those. Then we go from negative to positive, so we count it. Okay, so p of x had 2 sign changes. So 2 places where it changed from either positive to negative or negative to positive. So this means, so you have 2 real zeros, or real positive zeros. So you have 2 real zeros that are positive, or you can keep subtracting 2 from it. Now think about why we would subtract 2. So do you remember that last theorem I just told you, the conjugate theorem, the complex conjugate theorem? That's why we're subtracting 2, because if I had a complex answer, they go in pairs. Okay, so we have 2 real positive zeros or 0 real positive zeros. So 2 or 0. Now if I started at 4, so if I had 4 sign changes, you would have 4, 2, or 0. Does that make sense? So you just keep skipping. All right, now let's look at p of negative x. And this is the part that people have the hardest time with, because p of negative x, you actually need to find what that is. So you need to go in and wherever you had x, put parentheses and put negative x. So we have negative x cubed minus 3 times negative x squared minus 4 times negative x plus 12. And we need to simplify it out before we count the sign changes. So I have negative x being cubed. So if I had a negative number cubed, it's negative. So you have negative x cubed. The next one, if I have a negative number squared, it's positive. So I just still have negative 3x squared. Is the negative out in front of the 3. The next one I have negative 4 times negative x, so that's plus 4x. And the last is plus 12. So if you count the sign changes on this one, you go from negative to negative, right? Negative x cubed, negative 3x squared. Then you go from negative to positive. And then you have positive to positive, right? So you're just looking at the sign out front. Is this making sense? No. Do you understand the sign change thing? So you're looking at the numbers out front, negative, negative, plus, plus. So you look for where it changed. It went from negative to negative, so that was okay. But then it went from negative to positive, so we count that. So we do like a little swoop underneath it. All right, so what this means is that, so p of negative x had 1 sign change. And you don't always have to write out all this information. I'm just doing this for your notes right now. So p of negative x had 1 sign change. So there is one negative real 0. Now, same kind of thing. If I had 2, I would subtract 2 from it, so I'd have 2 or 0. If I had 3, I'd have 3 or 1, right? You're always skipping the number in between. If I had 5, it'd go 5, 3, 1. Okay, but we just have 1, so we stop there because we can't have -1 negative real zeros, right? You can't have a negative number of real zeros. Okay, so we stop. Okay, so then we fill in a chart. So I usually do plus, minus, and then C for complex or imaginary. You can put a little I too, or instead if you like the I better. Okay, and you're going to pair every answer from the first one with every answer from the second one. Okay, so I could have 2 and 1. I could have 0 and 1. Make sense? So 2 and 1, 0 and 1. So 2 and 1, 0 and 1. You're pairing every number here with every number here. So you could have 2 and 1, right? 2 and 1. Or you could have 0 and 1. Okay, it gets kind of tricky if you had like 2 and 0 and 3 and 1, because you could have 2 and 3, 2 and 1, 0, 3, 0, 1. Do you see what I'm saying by pairing each one with the other one? Okay. Now, what was our original degree? What was the degree of the polynomial? 3. So that means that the most number of zeros I could have, right? Well, the total number of zeros I should have is 3. So now if you read across these rows, if you had 2 positive and 1 negative real 0, how many complex zeros would you have? 0, right? Because you're going to add up to be 3. So you have 2, 1, there's none left. How about the next row? So if you have 0 positive and 1 negative, how many complex would you have? 2. And that's what I was saying, that's why they go down by 2, because these complex zeros have to be like 0, 2, 4, 6. They go in pairs. Okay, so that's your chart, so you need to know how to compute those charts. Yeah, Santiago.
You wrote 2 real positive zeros for 0. Where'd you get that 0?
This 0 here. Because in the definition it says the number of positive real zeros of f is either equal to the number of variations in sign, so that was 2, we had 2 sign variations, or less than that number by an even integer. So in other words, keep subtracting 2 until you get the last positive integer, or 0, I guess. Right, so you start at 2 and keep going down by 2. So you could have 2 or 0. If you started with 6, it would be 6, 4, 2, 0. What did I do to what? I think that's what you were just asking too, Izzy. So in order to find C, you're looking at the rows in the end. The rows need to add to 3.
Why?
So that's your degree. So you need to have 3 zeros in all.
So you just fill in whatever number is necessary.
Mhm.
So if you had like a 0 and a 0, you put in a 3.
Yeah, but it would never be 3.
Yeah, but for like some weird example.
Yep. Yeah, it's always going to be even numbers for your complex numbers because they go in pairs. So if you have 2i, you're also going to have negative 2i. They go in pairs.
If you started with like x to the 4th, would they need to start adding a 4?
Yep. So if you started with x to the 4th, they add to be 4. All right, so next one. So we have x to the 5th, so that means those rows are going to add to be 5. So we look for a number of sign variations. So we go through, we have plus to minus, so there's one there. Then we have minus to minus, that's okay. Minus to plus, plus to minus, minus to plus. Do you guys see how I got that? Okay, so we had 4 sign variations. So that means there are 4, 2, or 0, right? So start at 4 and keep subtracting 2. 4, 2, or 0 positive real zeros. Okay, now we need to find p of negative x. And like I said, this is where people make the mistakes because they have trouble computing p of negative x. So p of negative x, everywhere you have an x, you're going to replace it with parentheses negative x. So you get negative x to the fifth, so that's negative x to the fifth, right? It's negative in the end. Negative x to the fourth would be positive, but then you have that negative out front, so it's negative. Negative x to the third is negative, so you'd have a negative times negative 6, so you'd get positive 6x cubed. Negative x squared is just x squared. So you get plus 14x squared. Negative 11 times negative x is plus 11x, and then plus 3. Basically, if you guys get really good at these, the only signs that change are your odd powers. The evens stay the same. So see how you went to negative, positive 6x cubed, and then positive 11x. The rest all stay the same. All right, so number of sign variations. So go through, you went from negative to negative, so that's okay. Negative to positive, so there's a sign variation. Positive to positive, positive to positive, positive to positive. So there was only one. So that means there is one negative real zero. So think about how this would help if you were trying to find all the zeros. Once you find one negative real zero, you know you don't have to try any other negative numbers. It has to be positive. All right, so we have plus, minus, complex. So every number on the top, so 4, 2, 0, is going to pair with 1. So I'm going to have 4, 1, 2, 1, 0, 1. And then your rows need to add to 5. So you have 4, 1, so you have 0 left for complex. 2, 1, so 2. 0 and 1, so you have 4 left for complex. See how it works? So that's your possibilities. So that's your chart. Yeah.
I'm confused about time. Hey, go back. Okay, so you see how there's
Shh, guys.
4 sign variations, so there are 4, 2, and 0 positive numbers. Where are you getting 4, 2, and 0?
You always start with the 4, and you keep subtracting 2. So you have 4, 2 less than that's 2, 2 less than that's 0. You can't go any more. Like if you tried negative 2, we don't say that there's a negative 2 number of real zeros, right? That's weird. You can't have a negative number of zeros. So you always stop at 0. Now with the 1, if you subtracted 2, you'd be at negative 1. It's the same kind of thing. You can't have negative 1 real zeros. Okay, so that's the only one. Does that make sense? Okay, so let's try another one. I don't know if that's your last one. Do you guys want to try this one first? See what you get? All right, so when you guys did this, you looked at your positive sign changes, or number of sign changes. So you had 2x cubed to negative, so that's positive to negative. Then you have negative to positive, positive to negative. So p of x has 3 sign changes. So there are 3 or 1 positive real zeros. You don't have to write this. I mean, you can just put it on the chart. It's fine. All right, now p of negative x, when you compute it, you have 2 negative x cubed minus negative x squared plus 4 times negative x minus 7. So when you compute it, your negative, if you had a negative number and you're cubing it, you get a negative number in the end. So it's negative 2x cubed. If you have a negative number and you're squaring it, you get a positive number, but then you have a negative out front. So it's negative x squared. The next one, 4 times negative x is negative 4x, and the last is negative 7. So you get 0 sign changes. So that means there's 0 negative real zeros. So on your chart, you're going to have 3 or 1, and they're each paired with a 0. So your number of complex zeros is going to be 0 or 2. So that way your rows add to be 3. Now I will say the thing that gets kind of weird on Descartes' rule of signs, let's say you do end up with 1 and 3 over here. And you're like, what? How did I get 1 and 3? Like when you're computing it all out and that's what was left. Sometimes, if you look through at your answer, let's say this was your original, then what else is a 0? So if this was my original polynomial, do you guys see that you could pull out a factor of x? So what else would be a 0? Yeah. 0 would be a 0, right? X equals 0. So that means that that wouldn't be positive or negative. So that gets kind of tricky. So if you do see something weird going on over here, and they're not going in pairs, it's not going 0, 2, 4, check to see if x equals 0 is a 0, right? Maybe that will happen. So just be aware. All right, so do you feel pretty good about these? Okay.
How should we is our final answer the chart?
Final answer is the chart.
Okay.
Yeah, in the next section we're going to actually find zeros. So this could be useful if we were finding zeros. Because do you remember how we used synthetic division to check to see if certain things were zeros? We're going to do something like that. And if we find one that's negative, and it was like number 2 where we only had one that was negative, then we stop trying negative numbers. Or like number 3, if we knew that there were no negative answers, then we don't even try any negative numbers. We only try positive numbers. So it can save us some work.